Hi, and welcome to our lecture tonight on Martin Aston on Engineering the Future, a System of Systems approach. Martin Aston is a chartered engineer with over 40 years' experience in the aerospace industry. He joined British Aerospace as an undergraduate apprentice in 1980, spending the first year on the shop floor learning how aircraft are built and operated. Having graduated from Southampton University with a degree in aeronautics and astronautics, he began his career in the wind tunnel department at the Filton facility near Bristol. Over the next 15 years, Martin carried out a number of engineering and project management roles within BAE Systems Airbus division, concluding accountability for all test capability within the Filton organisation. When the Airbus single company was formed in the early 2000s, Martin took on responsibility for delivering UK wind tunnel testing within the wider Airbus business. His career took another turn in 2005 when he was asked to lead a large research programme investigating the digitalisation of engineering. This led to the formation of the CFMS organisation, and Martin was seconded from Airbus to set up and lead that new business. During the time, he sat on several UK and European Commission strategy committees defining the future of digitalisation within engineering. CFMS continues to be a key player in the field of digital engineering development. On return to Airbus in late 2012, Martin continued to lead a number of large, multi-partner, collaborative research programmes aimed at developing the engineering capability needed to deliver the next generation of aircraft. Since 2008, he has led the Brunel Challenge. This is an ambitious UK-based initiative aimed at delivering transformational change in engineering capability across a range of industrial sectors through the adoption of advanced digital technologies. Having left Airbus at the end of 2020, he now provides specialist support to organisations seeking to develop and exploit innovative, digitally enabled engineering processes. He continues to be an advocate of the future of engineering and the need to inspire young people to see engineering as an attractive, rewarding career. Martin is married with 2 sons. He enjoys sailing when time allows, exploring Scotland and listening to music. I'll now pass over to Martin for the lecture. Enjoy.
So with no further ado, let's get cracking on the presentation itself. So in terms of what we're trying to achieve, and part of this is what I'm doing with Brunel Challenge, but it's also, if you like, a call to action for the whole of engineering, because what we have to do is solve the societal challenges that we face through world-leading engineering excellence. That might sound ambitious, but hopefully by the end of the presentation, you'll realise that this isn't a nice to have, it's something we've got to do. It might seem strange that I open this presentation to explain what engineering is. Over the past 5 years that I've been working on this topic, it's been incredibly frustrating that engineering seems to be one of the most misunderstood words in the English language. People just don't seem to understand what engineering is, and it's not helped by television campaigns such as the one with a certain energy provider that is telling you that an engineer is going to come and fix your boiler. That's fundamentally wrong. It's a technician that will fix your boiler. The engineer actually designed the boiler in the first place. So what we've had to do is to put in simple terms, explain just what engineering is. And the way we put it is, as you can see on the slide here, hopefully, which is where science, ambition and imagination become a tangible, viable product. So we take science, but as you can see from the picture in the middle, and there's a whole raft of reasons for that picture that we've chosen, engineering is a combination of analysis, but also creativity. I think a lot of us forget that engineering is not just about the maths. It's also about creativity, and as we go through this, you'll see that the creative side of engineering is going to have to become far stronger in the future than it is today. Because as you can see on the right, we are very much at a turning point in engineering. We're going from products that we understand to products that are radically different to what we've seen before. And that means that engineering is going to have to change, that engineers are going to have to change. But let's put a bit more sort of meat on the bones of what it is we've got to do and why. So why should people care about engineering? Well, This is a picture that shows the CO2 levels in the atmosphere, but also how the temperature of the atmosphere is changing. That picture there was generated by scientists. So as we saw in the previous slide, scientists are the one that actually set the agenda, but delivering the solutions is down to engineers. Scientists themselves don't know the answer to the problems they're identifying. So we see this slide here that says, here's the CO2 in the atmosphere, here's how temperature is changing. They've given us the information we need. It's now up to engineers to actually develop the solutions to actually address that climate change problem. But that's from a sort of if you like, a societal point of view. But in terms of raw finance, this is a study that was done by the Ford Motor Company back in the 1980s. It's an incredibly influential slide. What's quite sad is that this has been around since I think 1982, yet people still find it surprising. But what this picture is trying to show is how influential engineering is on the overall life cycle cost of a program. And as you can see, although the actual design activity only costs about 5% of the project costs, it actually influences 70% of the overall project costs. Everybody talks about the need to improve manufacturing, productivity and such like, but as you can see here, you can only actually influence 5% of the project costs by the time you get into the production phase. So it is really important that we get the engineering right, because if you make mistakes in that early design phase, you then live with the consequences for many, many years. So this just goes to show, why is engineering important? It's what's going to actually solve climate change issues, but also from a purely financial and commercial point of view, you can actually take businesses down if you get the engineering wrong. So we said at the start that our ambition is to actually address the societal challenges that we face. What's quite interesting is I've been giving similar presentation to this for probably about 18 months. Some of this slide has stayed the same, but in the last 12 months, some of it has radically changed. But we can still cluster the challenges that we face around three areas. So societal, technical, and then the sort of commercial, political type. So from a societal point of view, there is increasing awareness now of the effect that the human race is having on the planet in terms of both the climate, but also pollution. We talk a lot about plastics and the concern that people are having. What's quite interesting is people talk about saving the planet. I think what people don't realize is that the problem we're actually trying to solve is to save the human race. Nature has a very good way of actually correcting itself, and the way nature might correct the planet might not be compatible with the way we want to live. So we really do need to address this one. But the other thing that is quite interesting from a societal point of view, and this has probably changed over the last 12 months, is the fact that people's career ambitions are changing. And as we've seen over the last 12 months, working practices are changing as well. If you look at the sort of traditional engineer, maybe I'm one myself, it tended to be a job for life, and you gathered experience over a long period of time. But increasingly, as we look towards the next generation, the younger people around now, they don't necessarily want that job for life. They want choice. They want to see different careers. There's studies being done into this around the so-called Generation Z. And it's saying there that they probably want 2 or 3 careers in their lifetime. And that's not just jobs, that's careers. So as engineering and as organizations that rely on experience, rely on knowledge, how are we going to actually accommodate that desire of those people to actually change jobs far more frequently? We also have some very interesting technical challenges. So as we move towards the next generation of products, we as engineers will be expected to get those products right first time, even though the technology is radically different. The financial model that most businesses now operate just could not tolerate the sort of level of failure that we saw in the sort of 1950s and 60s. It's all well and good doing an incremental change and getting it right first time. So I'm always amazed that the first flight of any Airbus or Boeing aircraft, for that matter, They go up in the air and they're up there for 4 hours. It's quite incredible how good the product is out of the box, but we forget that we've got decades of knowledge of how to design an aircraft of that type. If we're to do the same for a hydrogen powered aircraft or a distributed propulsion type aircraft, would we still be able to fly it for 4.5 hours on the first flight? I don't think we could. The other challenge we've got is the only way we're going to get the performance improvement that we need is through far greater integration of technologies within the overall product. So the picture that we've got there on the top right is for effectively a distributed propulsion aircraft. As you can see, the propulsion system is far more integrated into the overall airframe of that aircraft. At the moment, if we want to change the engine specification, it's a relatively straightforward process. The engine is treated largely as a black box under the wing in most cases. But if you look at an aircraft of that type, if we touch anything on the airframe, it will affect the propulsion system and vice versa. So how do we actually design and engineer that aircraft with such tight integration between different organizations, different disciplines and different technologies? And then finally, there's the question of assurance and regulation. The picture there is of a car without a steering wheel. We deliberately choose this as an example to demonstrate the complexity of the problem we face. That is an autonomous road vehicle. There's some work being done in the United States by the insurance industry that's looking at what needs to be done to actually demonstrate safety, demonstrate compliance with existing legislation. In order to demonstrate compliance of that vehicle, that autonomous road vehicle, with current regulations, you would have to drive that vehicle 11 billion miles and it would take 500 years. So quite clearly, that's not a viable option. So our traditional approach of physical testing, cycling through a series of cases, just will not work. The reason it's going to take so long is that the sheer number of variables is huge. And the thing is, by the time we get to 500 years, chances are the technology will have changed anyway, so we'll have to start again. So clearly something has to be done in terms of the way we actually define regulations, but also the way we demonstrate safety. Safety is not negotiable, so we're going to have to find a way to address that. Moving on to the commercial and political challenges, you can probably rewrite this section every day, but certainly what we're seeing is increasing globalization, but also a worrying sign that is coming out now is protectionism, and that protectionism is accelerated by the current COVID crisis. We only see what's happened recently about the vaccine situation to realize that we're operating in quite a different environment all of a sudden. But the way we actually develop these products, the supply chain is truly global, and we need to understand how that's going to operate in an increasingly complex political landscape. But it gets even more complex because we talk about sectors, people talk about the aerospace sector, the automotive sector, we talk about the power sector. The picture on the bottom left there is of an Airbus flying car, and the question is that an aerospace product? Is it an automotive product? Or if you talk to somebody like Uber, they'll say it's none of those, it's a digital platform. So clearly the way we actually manage ourselves as industry, but also actually manage ourselves as technology is going to have to change. We've got to stop seeing ourselves as aerospace engineers, as automotive engineers, and just realize that in the future, engineers are just that, engineers. But I think we shouldn't see this as a problem. There's two versions of this slide. This is saying these are the challenges, but every challenge is an opportunity. And what we should be seeing is, as engineers, that this is an absolutely brilliant opportunity. There are problems to solve. There are opportunities for new technologies, new products. And so this should be seen almost as a wake-up call that says, look, we've been comfortable with where we are, but now the future is very different and we've got to adapt accordingly. And to put that into context, this is a slide that we've made a lot of use of within the work we've been doing on Brunel Challenge over the last few months. It's proved very influential because I think until we put it in this format, a lot of people didn't realize both the challenge and the opportunity. This is a product life cycle S curve. It's a well-established process, if you like, of mapping technology and maturity against time. There's lots and lots of academic papers on this. But what we can see here is that the actual market and also product innovation changes over time. I'll deliberately start on the right-hand side of this picture because that's where we are at the moment in a lot of sectors. When we get to this part of a product life cycle where we understand the market, we understand the technology, we're looking at incremental improvements, then in that phase, the way we get business advantage is through improving our production productivity. We've been there in aerospace and also nuclear for decades. If you look at today's aircraft, they're largely a refinement of the Boeing 707. It's not radically different from an architectural point of view. There's clever technology on it. There's clever materials. We've got fly-by-wire and all sorts of other things. But fundamentally, the product hasn't changed completely since the 1950s. Similarly, in nuclear, we're still talking about fission as the nuclear process. So the whole industrial ecosystem and the culture within industry is very much set up around that side of the product life cycle. What's interesting is the iPhone is an interesting example to see how that has already gone through this life cycle, and Apple are now finding ways to actually just do incremental change on the iPhone. They're having to look at ways of making it cheaper to make business benefit from it. But if we then go to the left-hand side of the curve, this is where there's far more disruption. This is where there's innovation. This is where engineering becomes paramount and engineering excellence becomes paramount. This is where there are high risks. If you, as we saw earlier, 70% of your product lifecycle costs, and that's a big life cycle, as you can see on here, are locked in at that stage of the process. This is where a lot of the opportunities are. We don't necessarily understand what the product looks like. We don't necessarily understand what the market is. And so there's a huge number of variables and hence high risk. Now, it's interesting to note that from an aerospace point of view, and as we can see on this slide from a nuclear point of view, but it's other sectors as well, the last time we experienced that level of disruption was in the early 1950s. So 70 years ago. So people, including myself, who've been involved in industry for many, many years, have never experienced that type of environment, that culture, when you've got a completely blank sheet of paper in front of you and somebody says, come along and do something really clever. And this is why we need to invest in our engineering capability, because the culture, the type of engineers, the type of engineering that we need in that phase of program development are quite different to what you have at the other end. It doesn't mean to say that people can't adapt, but I think we need to actually make use of our young people. They tend to be far less set in their ways. They're probably more used to dealing with that level of uncertainty, but we need to balance that with experience and knowledge. But certainly, I think what this slide shows is that we are on the verge of quite a change in industry and quite a change in engineering. And that's made even more complex by the fact that we're going to have to make sure that our products operate as part of a system of systems. So this slide here was intended to explain to people why achieving net zero is actually far more complex than people think. There's a lot of talk about net zero, and people are saying we're going to achieve net zero by 2030, 2040, 2050. They all pluck dates out of the air and say they're going to do that. But to actually truly achieve net zero is phenomenally complex. So this particular example we got on the screen in front of us is of a hydrogen powered aircraft, but we could have chosen an electric car or all sorts of other things in there. And so when people say an electric car is good for the environment, what they tend to talk about is the actual point of use impact on the environment. So yes, there aren't noxious emissions coming out of an exhaust pipe. Although what's quite interesting in the automotive sector is they've now discovered that actual tyres and brakes generate significant levels of particulates. So although they've got rid of the exhaust pipe, they've yet to get rid of the tyres and brakes. But let's talk about this aerospace focused example of a hydrogen powered aircraft. So when we look at that aircraft, we think, yeah, okay, it's great for the environment. But what we have to realize is that if that is powered by hydrogen, that the hydrogen has to come from somewhere. The process to produce hydrogen requires lots of energy. It's incredibly reactive, although it's the most abundant element in the universe. It's also very good at latching onto other things as well. So to generate hydrogen takes huge amounts of power, be it nuclear, be it wind. However we do it, we're going to need a lot of power. There's then the actual production process. We've actually got to make the production processes, the facilities to actually do that. So there's an environmental impact of actually generating that infrastructure that goes with it. We've got to distribute it around the place, because I'm not aware of any airport, certainly not in the UK, but probably not in the world, that has a hydrogen supply on tap. So how do we actually distribute the hydrogen to enable it to be used on the aircraft itself? Then there's the ground operations. So although we might have a hydrogen powered aircraft at the moment, we've got lots of diesel powered vehicles chuntering around the airport. Quite often we've got diesel powered buses going to and from the airport. So we need to consider the actual impact on the environment of getting people to and from that aircraft. We need to think about air traffic management and the airspace we're in, and actually how we impact on the atmosphere. So although the aircraft itself might be producing zero emissions from the engines, the way it actually interacts with the atmosphere might have other implications that we need to consider. And on the right hand side, we can see the actual production process. So there's been a lot of talk in the press about rare earth metals used in battery production, but no matter what we make, the materials have to come from somewhere. So we either dig them out of the ground or drill for them. So we need to consider the environmental impact of actually gathering the raw materials. We then have to move it, because you don't often process the materials actually on the mine site or the oil rig. So we've got to distribute those materials, and then we make components. So we have to find ways. There's energy involved in actually producing components, and then we've got to distribute them. Sometimes they go all around the world, several times in some cases, from actual component production through to final assembly. And then what we also must consider as part of this overall system of systems is how we get rid of things at the end of it as well. So as engineers, when we design that product in the middle, increasingly we're going to have to consider the effect of all those other parameters that we can see around it. Now, at the moment, that isn't the way we do things. This is why engineering is going to become far more of a systems challenge than it is today. And the techniques, the tools we need to actually enable us to do this for real just don't exist at the moment, or if they do, they're not powerful enough to enable us to actually understand the implications we have at other parts of the system. So here's an answer. And as you saw in the introduction, I've been promoting the idea of digitalisation in engineering for some time. But I think the point we need to raise here is this isn't a case of digitising today's engineering process. If you look at how we do engineering today, it hasn't really changed for decades. In fact, it probably hasn't really changed for hundreds of years. It's still a very transactional, sequential process. So the analogy I use is to compare a landline phone with social media. So if you look at a landline phone, it's actually quite similar to the way we do engineering today. So if you want to arrange a weekend away using landline phones, you ring your friends one at a time, you talk to them individually, they do their own analysis of the problem, and they get back to you when they've finished. If you're lucky, the holiday is still available by the time that process is finished. It's very error prone. If people misinterpret what you're saying, they can then do the wrong analysis and they could be late in delivering that information back. The alternative is to set up a WhatsApp group, and then you can talk to everybody immediately in real time. You can use different forms of data. You can do different analysis. You can communicate by voice. You can communicate by text or words, or you can even put videos and pictures and all sorts of things in there. So when we talk about digitalization, it isn't just applying digital to how we do things today. It is a complete cultural change in how we do things. And this is why when we talk about engineering the future, actually it's the future of engineering that is going to have to change to enable us to do this. So what digitalization will enable us to do is to actually co-create products. At the moment, we tend to pass information between organizations. It's quite a crude process. We tend to use email a lot, which is almost untraceable. So from an assurance point of view, it's not pretty good. But in terms of the actual integration as well, if we can co-create these products in real time using digital systems, we have to think about things like security. We need to think about provenance and such like. But the opportunity is there, and this is why we need to do the research to actually understand how to do that. Regulation and validation is key, and we need to find other ways of validating the products that are less dependent on complex, time-consuming and expensive physical testing processes. We should be thinking about far greater use of mathematics. We've got greater computing power. Let's look at statistical and mathematical analysis to enable us to predict the future. But also let's think about smart testing. So rather than actually validate the product, can we start to validate the design process as well? Again, digital techniques enable us to do this. Let's do simulation far more, but this isn't just a case of simulating airflow and materials properties. We need to simulate the entire system. So we need to simulate the production process, probably also simulate the operational environment as well. So when we talk about digital twins and simulation, this isn't just a case of running a few CFD cases. This is actually looking at a complete digital twin of real life. Phenomenally complex. We need to find ways of being far smarter on that because it's going to get too expensive if we try and do it the way we do it today. And then finally, collaboration and education. This is closely linked to the co-creation activity, but we're going to have to find ways to collaborate far more across the entire supply chain and across engineering. The picture there is of an orchestra, and I use this as an example of showing how individuals can actually collaborate and co-create. It also shows the future of engineering, because although we use the word engineer, you don't use the word orchestra. An orchestra is a collaboration of musicians, each with their own domain specialisms, but they cannot operate in isolation. So going forward, we might still use the word engineering, but an engineer will be very different things within the perimeter of engineering. So you will have data scientists, you will have aerodynamicists, you will have material scientists, but they will all be part of this engineering orchestra, all working together towards achieving a common aim. So just as an orchestra wants to produce nice music, what we need to do as engineers is to produce attractive, excellent products. And that's why I use the word education as well, because if you look at the education system we have today, it tends to teach people how to be good at a specific topic. It's not very good at teaching people how to operate within an ecosystem like an orchestra. And it's something we do need to consider. If you look at an engineering degree today, it's probably almost identical to an engineering degree that was taught in the 1960s. But when we start to look at digitalization, is that method of teaching, is the actual scope of that degree still the right thing to do? I don't have the answer, but it's certainly something we need to think about. Bit of light relief, because the education point is very important, because we need to actually inspire people to become engineers. What's quite worrying is how unattractive engineering is as a career. I was involved with the Bird of Prey program at World Skills, well, it's actually over a year ago now. These young people just really didn't understand what engineering is. They saw it as difficult. They saw it as, some of them, quite boring, and I think a lot of that is around the way we actually teach it. So what we did here was we actually built a model of this aircraft concept, not only to show a possible signpost to the future, and please don't tell me what's wrong with this, because we know there's lots of things on it that aren't technically correct. But the idea of it was not to actually demonstrate what an aircraft of the future will look like. It was there to show that it's going to be different, but also to get people thinking that this is going to be exciting. This is going to be different to how it is today. And it gives me the opportunity to do new, exciting things. And certainly, it certainly made quite an impact. And yes, the question we're asked more than anything is, why is it orange? Because most aircraft are white. So it just goes to show that by deliberately being controversial, you can actually inspire people to think differently. And that's what we've got to do. So I've talked a lot about the Brunel challenge. The idea here is that we have a national program of engineering capability development that's very ambitious, that embraces digitalization and cuts across all sectors. It's still being scoped. It's quite sad that it's taken us so long to get to this point, but we're working very hard and we're getting closer to actually launching this. As you can see at the bottom there, with all the logos that you can see, it covers all the major sectors in UK industry. In fact, there are other sectors as well that are involved that aren't in the logos. These are the core organisations, if you like. But what we want to do is to deliver a new type of engineering and a new type of engineer. And the way we want to do that is through a program of what we're calling breakthrough projects. So what we want to do is put real engineers into real challenges to actually both develop and experience new ways of doing things. The idea is of forming so-called rainbow teams, where people can actually be given the opportunity to work with people that normally they wouldn't get any chance to work with. And by doing this, what we're hoping is for the UK to become global leaders again in engineering. If you look at a lot of the historical and the legacy we have in terms of steam engines, jet engines, even the digital computer, the UK has traditionally been a good place to do engineering, and we see that as an important thing to go forward with. Unfortunately, engineering probably isn't seen in the right light at the moment, but certainly what we want to do in Brunel Challenge is to put engineering where it should be in the UK psyche. So a few takeaways to leave with, if you like. So I think it's important to know the importance of engineering. As we've shown in a number of the slides in this presentation, it's actually engineers that are going to define those products that will address climate change. If you watch the news, all you'll hear about is scientists. Scientists aren't going to deliver the solution. Scientists have solved the problem. It's now up to engineers to actually address that problem. But as we've seen before, there's a lot of issues, there's a lot of challenges, but every challenge and every change opens up opportunities for innovation and also growth. We shouldn't see problems as a problem. We should see problems as an opportunity and to do something about it. As we saw with the S-curve, lots and lots of sectors are facing a period of revolution, even disruption, after many, many years of evolution. That's going to call for a huge cultural change as well as a technological change, and that's not just going to happen organically. We need to actually assist industry and assist people in going through that change. We coined the phrase in Brunel Challenge that we need to re-engineer engineering. It's quite interesting that we've heard a lot of people saying it back, so there must be something in that statement. But the reason we've said that is that we can't just tweak how we do engineering today. It really does need a transformational change to actually deliver the capability to produce, to define, to actually demonstrate and assure the type of products we need to achieve net zero and various other things as well. What I talked about in terms of digitalization is a key part about that, but we also need to make sure we have the people that can actually continue to innovate, but also use those digital systems. And the Brunel Challenge we see as a once in a generation opportunity for the UK to actually reinstate itself as global leaders in engineering. There's an awful lot of competition out there now. Historically, we've been very good at engineering and we still are, but what we mustn't let happen is for engineering to slip down the food chain within the UK system. We've got a huge opportunity here. If we get it right, we will set ourselves up for decades, and that's the opportunity we should be chasing for. So thank you very much. I hope you found that interesting, and I'm sure, Amina, there'll be an opportunity to ask questions.
Yes, anyone with any questions, please feel free to put them on the Q&A now. No questions just yet.
It's obviously all totally clear.
I've got one myself. As a young professional, what's the biggest thing you'd say to consider when going into the future? So what to keep in mind?
What I would say to someone like yourself is to continue to innovate. Don't get set in your ways. Don't just follow the way everybody else does things. Recognize that you've got ideas that you can make a difference, and don't just follow the herd. You know, we need young people like you with bright ideas to actually deliver those new products. You know, if you think back to the 1950s, and everybody says, oh well, that was the 1950s. If you actually look at the old black and white films, you don't see old people. They're all young people coming up with clever new ideas. And at the end of the day, the future is your responsibility, not mine. You know, I've had my career. I've done my bit. Delivering those new products that actually solve the climate challenge is now your job. So continue to innovate and see that you have an important role to play in that.
We've had another question come up. How do organisations or individuals get involved in the Brunel Challenge?
So at the moment, the best way is to contact me. So I think, I mean, my email address was on there. We are in the process of actually setting up an outreach activity, but at the moment, the best way is just to contact me. I know it's a bit crude, but that's the only way we have.
Another one. Do you think the government understands these needs and will support/fund it?
They're starting to understand. We've been trying to educate them now for best part of 5 years. I would say it's not just a case of does government understand this, does industry understand this as well? And if you look at that S curve, the majority of people in industry have only ever experienced the mature phase. You know, they haven't lived in that disruptive phase. I think we have a fundamental problem in government in terms of recognizing engineering as an important subject. They focus very much on manufacturing, probably because that's where we are in that life cycle. But I think there is also an element that that engineering is intangible, and people like to be photographed next to something, and it's very hard to be focused or photographed next to an idea. So we are working very hard. We've made huge progress in terms of educating them, but I don't think we're there yet, which is why everybody on the call needs to make sure the government knows how important this is.
Thank you. And there's another comment saying, thank you, brilliant presentation. How do you think software is going to play a role in the future, particularly the hardware/software balance?
Right. I think we need to stop thinking about hardware and software. If you use an app on your phone, you don't think about the software that's behind it. And I think we need to start thinking at the effectively digital capability. It's going to change radically, and it changes incredibly quickly. And what we need to be able to do is exploit digital. One of the problems we've got at the moment is that the way we treat digital systems within engineering tends to be very long term, and it's very software heavy, shall we say. It needs to be far more agile, just as social media is constantly changing, just as other digital platforms are constantly changing. And we need to understand how to use that. So as quantum computing comes online, how do we use that? As more distributed computing systems come online, how do we use those? So I think we need to stop thinking about software and hardware and start saying, what can digital do for us?
Thank you. We've got a question from Tim saying, how does a traditional business move away from established technology to new ways whilst maintaining its existing commitments?
Really good question. I don't think there's an easy answer to that. And I think it's one of those things that we need to, there's a balancing act to be done. If we just carry on doing things the way we do today, then you become the world's best at what you do. What I always say when discussing this type of point, and it is an incredibly serious point, and I'm not trying to trivialize this, is imagine what you were like when you were the world's best slide rule manufacturer, when Clyde Sinclair walked in the room with his first very crude electronic calculator. Suddenly you became obsolete overnight. And I think there is a balance here. I think it's understanding how do we get those opportunities into business. And I think this is why initiatives like Brunel Challenge are so important, because there are risks with changing business models. There are risks with changing the people, the skills within our organizations. And initiatives like Brunel Challenge will de-risk the business process. But I don't think there's any simple answer to this, I'm afraid. It's something we've got to work on.
Thank you. There's another one from Dan saying, in a world where the increased regulation and costs associated with demonstrating compliance, how do large engineering companies stop themselves from restricting innovation to reduce risk and cost associated with new developments?
Brilliant question. And that's why we've got to totally change our approach to regulation and compliance. We've got to work with the regulators. But that example I gave of the autonomous road vehicle, if you've got to drive it 11 billion miles, if it's going to take 500 years, it's just not going to happen. Now, society will want technological advance. So we have got to find a way to do this. We've got to use mathematics far more. And there are people who are already looking at clever ways of doing mathematics to predict the future. But what we've got to do is recognize that we've got to do something about it. Don't just pretend that the problem will solve itself. It won't. We need to look at new ways, which is why we're saying re-engineer engineering. So within Brunel, it's probably the one we've talked about most of all, because it is a big challenge. We cannot compromise safety, but we also recognize we can't carry on doing it the way we're doing it today.
Then there's another one that's quite interesting, saying, do you think there is a limit to how much one can innovate?
No, I really don't. And I think a lot of it depends on how you define innovation. I think innovation isn't a big bang. innovation is a whole range of different levels, and you can do something very small that is phenomenally innovative. I still find it's interesting how big companies, and as I no longer work for a big company, I can probably say this, where they lock people in a room and say, go away and do something innovative. If you want to do something innovative, sit at home and think about something and you'll come up with a brilliant idea. I'm sure some of the world's best innovation did not take place within a work environment. It's just that spark. Now, what matters is what we then do with it, because there's no point in innovating if all you do is keep a really good idea and it goes nowhere. And that's the bit we're not very good at the moment. I think we're very risk averse, and we also look at the potential financial implication of failure. We've got to change that. We've got to go back to being real innovators. And
they've just followed that question up with, is there a boundary beyond which it is possible to innovate/improve further because it'll just become too risky or complicated?
If you continue to apply our current economic models, yes. If we start rethinking our process that says actually what really matters here. So if you look at that system of systems model to address net zero, it could be that some parts of that are very expensive, very risky. And what we need to understand is how do we actually share that risk across the entire ecosystem? And this is where governments have got to learn to work together, because this is a global problem. It's all well and good saying we want the UK to be net zero by 2050, but unfortunately, we are not the only ones on the planet. So we could be beautifully net zero, but if the rest of the planet isn't, it's an almost pointless exercise. So this is where that system of systems becomes key, and we need to understand the economic model that goes with it.
We've got a couple more asking if do the Brunel Challenge sound similar to STEM initiatives? Does this mean the existing STEM programs need revitalised?
Brunel Challenge is just a program we want to launch. It's going to do its own program of work, hopefully. In fact, earlier today I was just writing some of the descriptions of the projects we want to launch with. I think we as an engineering community need to take STEM increasingly seriously. I think when we talk about STEM initiatives, it should be just part of the nation's culture. It's one of those things where, you know, it should be seen as interesting, it should be seen as exciting, and that should inspire people and get them to want to do things. We shouldn't make people do STEM subjects. They should want to do them, and I think part of the way we teach those subjects doesn't help, but also there's something about the way young people go through the education system that we seem to knock all of that excitement and innovation out of them. So we do need to do STEM initiatives, and we need to continue to do them more, not less.
The software industry has enabled low barrier to entry and a culture of experimentation to see what sticks. How can this be achieved in heavier engineering?
And that's one of the actual breakthrough projects we want to do in Brunel Challenge. This idea of being far more agile, understanding and not being afraid of failure. I think at the moment we are incredibly risk averse. If you look at the software industry, far less so, but they're not flippant. They do actually understand, they manage risk, and it's something we can learn from and need to.
Then there's another one asking, what needs to be done to ensure engineering degrees are different to ones back in the 1960s?
Brilliant question. It's a very, very complex and controversial topic. One of the things that doesn't help is the accreditation system, because each degree is accredited by organisations such as the Royal Aeronautical Society to actually say this is a suitable degree. So you've got to actually consider the accreditation system as well as the content of the degree itself. It's not something that's going to happen overnight, but I don't think we can ignore it. It's something we should be actively thinking about and looking at the education system and understanding that the topics that we taught people in the 1950s may no longer be as relevant as they were then.
Thank you. These are from Anonymous. So do you think existing large companies, e.g. Airbus, Rolls-Royce, will be radical enough to make significant change in the industry, or is it down to startups?
I can probably say what I think now, but I think there will always be a place for the big companies, but I think those big companies have to realise that they're not too big to fail. I think the best example there is SpaceX. And SpaceX has completely shaken the space launcher market. Okay, it's not a startup, but what we need to realise is there are people in the world now that actually have more money than some of these big, large industrial organisations. You know, there was talk today about Jeff Bezos and how much his net worth is. If he put his mind to it, he could launch a new aircraft development program today. He could use the best engineers in the world today. So I think rather than the sort of these companies being too big, too slow, I think they need to recognise that there are alternatives now, and there are people that can actually deliver the sort of product that traditionally they have quickly. They do have constraints. You know, it is very difficult to change big organizations, but I think they need to recognize it's something they need to do.
And we've got another one from Anonymous, which I think's along the same lines, saying in large organizations there is a significant amount of inertia and the desire to just refuse what we have because we know it works and it'll cost less than creating something new. Do you have any suggestions as to how engineers can influence businesses to change and see that a revolution is needed instead of evolution? Interesting question there.
Yep. Show them the S-curve picture, because that one picture says it all. Those people that are thinking that way, behaving that way, are doing so because that's all they've ever known. If you look at some of those large companies, they've been in that mature phase of the life cycle S-curve for decades. You know, if you look at where we are in terms of jet aircraft, they haven't fundamentally changed since the early 1960s. So those people's, their job has been around continuous improvement and refinement, but they need to recognize that the world is changing and that the product is changing, that the market is changing. So if anybody says, I don't need to change, show them the S-curve and say, the last time this happened was in the 1950s. It's about to happen again.
And then we've got one last question saying, should we be encouraging crossover between school subjects to encourage creativity?
I think all of this starts in schools, but also at home. I mean, we shouldn't put all the responsibility on teachers. A lot of this, the creativity, starts at home. When I was a kid, I always played with Lego. And I think there's a fundamental flaw with Lego now, in that it has special pieces. When I played with my Lego in the 1960s, it was all rectangular blocks and wheels and such like. So to get complex shapes, I had to be creative. I had to innovate. If you get a Lego set now, it's got all special pieces, so it looks pretty and everything else. And I think this whole approach to education needs to let young people think for themselves, because young people are very good at being creative and innovative, and unfortunately the education system seems to be very good at knocking that out of them. And I think let people, these young people right down to primary school age, have a bit more freedom. Don't constrain them, let them do their own thing more, and I think we'll see a huge benefit from that. But it's probably politically incorrect to say that, but that's what I think.
And we've got one, well, I think we'll squeeze in one last one from another anonymous person, which is quite relevant for today, saying, do you think the current COVID situation has / will cause a delay due to lack of available funding?
Good question. I think it shouldn't, but it probably will. I think it's a bit like your own finances at home, investing in the future versus fixing today's problems. I'd like to think that once we get over the immediate emergency, that government and business starts to look at long-term opportunities. We have to face facts. There's companies that are fighting for survival at the moment, and when you're fighting for survival, it's very difficult to think about what are we going to be doing in 20, 30 years time. I think the companies that survive and thrive will be the ones that actually find ways to actually innovate, to change themselves so they're ready for the future. But who knows? It depends how long this goes on for, I think, to really understand.
Thank you. And I'll just hand over to another member of our committee to say a vote of thanks.
Good evening, everyone. My name is Jayant Venkatesh, member Royal Aeronautical Society, Derby branch. Firstly, I'd like to take this opportunity to thank our speaker, Martin Aston, for this fantastic talk on engineering the future, a system of system approach. I found this talk very insightful and interesting. As part of me being a system design engineer, it's been it's such a brilliant talk because it covered most of the aspects of our day-to-day work. Some of the highlights that you gave, that is re-engineering, the need for re-engineering and innovation to be ready for the future. I think it's the key takeaway for me, at least. You did touch upon some of the challenges that we in the aerospace sector are facing, especially around the hydrogen-powered aircraft, which is on everyone's table at the minute. You touched upon some of the imminent things that we need to think about, such as air traffic management, the impact on our atmosphere. I felt that was pretty interesting. Battery technology, I think that's something that's been going on for nearly a decade now. You talked about lithium-ion battery. Well, lithium, they say it's the new oil. So really, I think this was I saw these things were something that I'm personally very kind of closely following as well. You talked about digitization as an opportunity, which was an opportunity, but now it's actually the need of the hour. So they also say digitization along with big data. So big data is the new gold now. So I think clearly you mentioned some of the things that we all have to keep an eye on. Bird of Prey was really fascinating, so I guess we've got to go and check it out. So for me, I've made a note of one quote that you gave: problems are not problems, it's actually an opportunity. So I think that was really insightful and brilliant. So without taking too much of your time, on behalf of our committee, I'd like to express my thanks once again, Martin, for taking the time out for sharing your views on system design with us. So thank you very much.
No problem. You're welcome.